Hi, everybody. Here we are with, I believe this is probably lecture 10. Most of today is going to be exploring the central limit theorem a little bit more. So I'm going to start by restating what the central limit theorem is. The central limit theorem tells us that if x is any random variable, quantitative random variable, does not have to be normally distributed. It can be, it doesn't have to be. So not necessarily normally distributed. If it isn't normally distributed, we can't use our normal distribution tools with it. Plus, taking a single observation is usually never the best way to do statistics. If you want to get more accurate results, what should you do? Yeah, so we're going to collect more data anyway, which is nice because of it dovetails exactly with the central limit theorem. Take a sample large enough, which generally means n should be greater than or equal to 30. And the mean of the sample x bar will be normally distributed. That's conclusion number one, because now we can use our normal distribution tools. And any normal distribution has two important parameters, the mean and the standard deviation. The parameters for the distribution of x bar, no longer an individual observation, but of a sample mean, are the expectation, which is going to be the exact same as the expectation of x. Because your best guess for what a sample mean is going to be will be the mean of the whole distribution. And the standard deviation of your sample means is going to be smaller with a formula, standard deviation of the random variable divided by the square root of the sample size. So those are our three conclusions. For us, the value of the central limit theorem is it allows us to use normal distributions to explore data by collecting a sample. If this weren't true, then collecting a sample we could find a mean, but we wouldn't be able to use normal distribution tools. And the biggest normal distribution tool is the two standard deviation. What's it called? Rubric? Rule of thumb. Yeah. So rather than sketch it again, I have the sketch in my previous notes. I'm going to show you in R what this might look like. I'll give you a second to get the rest of these notes written down. The part that tends to make sense to students is the fact that even if x isn't normally distributed, the means will be. That generally makes sense. The other part that generally makes sense is the center of those sample means is going to be the center of the random variable. The part that's really hard is the standard deviation piece. The idea that the sample means are spread out much less than the observations themselves. And one reason that's hard is we don't collect a bunch of samples. We do it once. We don't have all that time. I can't go out and collect 100 different samples of size 30. I do it once and then I use this. So we don't often see that the samples themselves do have a distribution, but that they spread out less than the observations do. So let's take a look. I guess I didn't need to move that. All right, so here's some data that I just generated randomly. It comes from a random distribution. Is this a normal distribution? How do you know it's not normal? Doesn't look anything like a bell. It's not even approximately normal. If we wanted to be fancy, we would call this bimodal because it's got two peaks, two places where observations are more frequent, but I don't really care about that. It's not normal, so we don't get to use those tools. Is it uniform? Talk with your neighbor and decide if this is a uniform distribution. Does anybody remember? Show me with your hands roughly what the probability distribution of a uniform distribution looks like. What does the probability of a uniform distribution look like? What does a graph look like? Yep, Ryan's got it. It's a straight line. It's a flat line, right? Because every interval has the same probability. This is not a flat line. It's not even close to a flat line. It's not a uniform distribution. This is neither of the two that we studied. We can still ask questions about it. For example, I can ask, what is the probability that an observation will be less than 10? But I can't use my normal distribution tools to answer this. What I have to do to answer this is just say, okay, well, how much data, let me see if this worked. Yeah, okay, how much data is less than 10 divided by how much data is there altogether? So there's a 42% chance from this distribution of getting an observation less than 10. It's actually not bad with technology. And in fact, there's some classes that don't even worry about parameterized distributions like uniform or normal because we can do it all with computers. And if you take Stat 244 with me, we'll be doing a lot of that. But I do think the idea of the central limit theorem is very powerful. Still, without a computer, that's not an easy calculation to find. Let me move this so you can see the whole thing. There we go. And in fact, you're going to do this in your lab. I'm going to ask what's the probability that someone has less than, 5 years of experience, or the probability that the city has less than 10 millimeters of precipitation or something. And you can answer it by doing a proportion, because this is a proportion based on data that we observed, which is our best way to get towards a probability when all we have to work with is data. If I want to do a normal calculation, what I can do is I can find means of samples, but let's just start by looking at the expected value of the distribution itself. Looking at the graph, what do you think the expected value is going to be? Doesn't have to be exactly right. You can say it when you have a guess. Finger. I like it, right? We can't be exact because we lose some detail when we go through a visual instead of the raw data. Yeah, but between 10 and 15 makes sense. Let's figure out what the actual mean is. About 12, right? Between 10 and 15. What's the roughly more or less the minimum of this data? 5 and the maximum? 20. So it's got a range of 15. It's spread out fairly big. Let's find the standard deviation, that single number that describes how spread out the data is 4.6. Right? Now, I don't get to use the normal distribution shortcuts with this, but it still has a mean and it still has a standard deviation. Now let's create a sample. Let's take a sample of size. I want this to work better, so I'm going to do 50 instead of 30. More data is always better. And it's very straightforward in R. You just say, I want you to sample it. And then you tell it what to sample and how many times to sample. R defaults to not replacing, but if we're treating this as a probability distribution, we do want to replace because we treat it as if the same observation can happen more than once. Okay, let's look at a histogram of that sample. Is that normally distributed? It is not. The central limit theorem does not say the sample is normally distributed. It says if you created a sample mean and you did that again and again and again, those means would be normally distributed. The mean of the sample, 12.9, which is pretty close to that 12.0. That makes sense, right? The mean of a sample should be pretty close to the mean of the whole distribution. So with R, I don't have to sample just once. I can do it again and again and again. I can do it very quickly by writing some code. This code is in your labs. You will be doing this. I'm going to have, let's do 10,000 samples, each of size 30. This is called a for loop. And it basically says, do this in the middle every single time for every one of these 10,000 sample means. We're going to do the sample mean is going to be, let me just do this. All right. Each time for every one of these sample means, we're going to sample our data and find the mean and store it in this vector. Here are the sample means. Oops. Right. Each one of those is the mean of one of the samples. How many means do I have total? I have 10,000 of them, right? And it took less than a tenth of a second. Computational power. Statistics is a computational science. Let's look at what those sample means look like. Is that a normal distribution? Absolutely. It's not perfect because this is statistics, right? But that's definitely a bell curve. What's the center of that distribution? What's the mean? 12. In this case, it is the center because it's nice and bell-shaped, right? It's the balance point is 12. Well, guess what? That's what it's supposed to be because the mean of the population itself was 12. And we can double check. There's the expected value of the variable, expected value of the means. I mean, it's a 10th off, right? Or a 100th off. It's almost exactly the same. It's not exactly the same. And why is it not exactly the same? Statistics, random chance, right? There is some randomness involved. Again, these pieces I find generally make sense. It makes sense that it should be a bell curve, and it makes sense that it should be centered at the same place. The hard idea is that it's spread out a lot less. So let's see if we can see that. Okay. Let's see if I can do this. That work? Yeah. Okay. I'll do it again. Okay, so I'm trying to fit two pictures in the same frame, so I got to zoom out a little bit. You're not going to be able to see the text very well. So the top one, that's our probability distribution. What's it spread out between, more or less? 5 and 20. And the standard deviation was 4.6. Right? The center here, you go up 2 standard deviations or down 2 standard deviations. It covers most of the data. Here's our sample means. Which one of those is spread out more? The top one, right? That was a quiz question. Look at a histogram, tell me which one is spread out more. What's our number that tells us how much a histogram is spread out? The single number, though. The range takes. The standard deviation is the single number that tells us how much our data is spread. So does the random variable have a bigger standard deviation, or does the distribution of sample means have a bigger standard deviation? The variable does. Let's find out exactly what that relationship is. Okay, so we had our standard deviation of the random variable was 4.65. The standard deviations of the sample means much smaller. How much smaller? Well, let's do the standard deviation of our sample and divide it by the square root of our sample size. Look at that, almost exactly the same. It's not exactly the same because it's statistics, right? This first one where I did standard deviation of the sample means in your lab, this is what I'm calling the experimental standard deviation. It's a number we compute from our simulated data. And this one here, this is the theoretical. This is what the theorem tells us. And they're close, but they're not exactly the same. Most of your labs will actually be farther apart than this because you don't collect as many samples and those samples aren't as large. But they'll be in a reasonably close, you're not going to see a 0.6 and then like a 13 or something. So again, that's the main point I want to make. Let's see if I can get the picture back. Still zoomed in too much. I'm gonna have to graph it again. The main point I want to make with this demonstration here, let's try it again. Sorry, that one and that one, is that your random variable can be spread out however. If you take sample means, 1, those sample means would be distributed normally. 2, they're centered at the same place. And 3, they're spread out a lot less. If you want an estimate of how much they're spread out, it's that formula, the standard deviation of your random variable divided by the square root of the sample size. All right. So last time we did it theoretically with kind of just an example. Today we've done it using technology and simulated data. And now we're going to do it using actual real data that this class collects. What's the hardest part of doing good statistics? Yep, so it's going to take us some time, but we're going to do it. I'm going to pause the recording, and by the time I start it again, we will have collected the data. All right, so you all threw that ball at the target, and what we've recorded here is the horizontal displacement from the target and the vertical displacement for the target. And we've organized by trials or by samples. Now, these sample sizes are not super big. That one looks like it's 11. This one's only 7. So our essential limit theorem, you know, it's not going to apply perfectly, but we might still get to see some interesting things. So first of all, let's just look. Here's our raw data. What do you think? Do you think we're spread out pretty evenly? Do you think it's biased? Do you think it's hard to tell just looking at all these numbers? Yeah, so what can we do instead of just looking at numbers? Make a visual, right? Move down that spectrum where our speed of understanding is going to increase, even if we lose a little detail. And here, the only detail we're going to lose is the specific number values. But that's all the throws. I've color-coded them by the first two trials, the second two trials, the third two trials. What do you think? Kind of, would you say there's a systematic bias? Yes or no, strong or weak? We don't have to say yes or no, but is there a strong systematic bias, or if there's a bias, is it a weak bias? Okay, yeah. So there, I would agree that there's a bias of balls being thrown toward the center because that was the goal. But I wouldn't say there's like a bias of missing up in this side or up in that side or down there, or even like vertical or horizontal. It's spread pretty reasonably well, and it seems to be centered pretty close to the target, which is pretty good. Right? So simply looking at data visually can speed up our understanding a lot. Right? What was the throw that was farthest off horizontally? About how much was that? 110, a little more than 100 centimeters. That's a lot faster than pouring through all of this data, right? Yeah. Exactly how much did that throw miss by? Your answer can be it's hard to say because we lost a little bit of detail. But we know that this red throw was closer than that blue throw, right? So we lose a little detail, but it really speeds up our understanding. We can get even faster with some understanding if we do what? That's for categorical data. Think about on that spectrum. Over here, we had raw data, which was low speed, high detail. In the middle, we had our visuals, which is moderate, moderate. And over here on this side, summary statistics, fastest understanding, lowest detail. So let's get some summary statistics. Here's what I'm going to do. I'm going to show you how I sometimes work with data. I don't use Excel a lot anymore, but I'm pretty fast when I do, even though this is Google Sheets, and so it's not quite as efficient. Oops. So what I'm doing right now is I'm just taking all of our data and I'm putting it in two columns. The first column is horizontal displacement. Missed some. And the second column is vertical displacement. It'll probably go even a little faster if I didn't have to worry about different sample sizes, but that's not a criticism, that's just life, right? Sometimes you don't find as many slugs. So there we go, we've got our two. This is horizontal and vertical. And let me just find the average. So that was our average horizontal displacement. That was our average vertical displacement in centimeters. How big is 0.42 centimeters? It's pretty small, right? Even 3.8 centimeters, that's less than 2 inches. Let's go ahead and put that on our visual, 3.85 and 4.29, okay? 3.85 and 4.29. And one of the nice things about Desmos is I can change some of that information. There it is. That was our overall average. How do we do overall in terms of the average? Pretty darn good, right? Very close to the expected value, right? If our expected value is hitting the dot, because that's what we're aiming for, then yeah, that's pretty unbiased. right? We weren't very far away. That was pretty darn accurate with our expectation. What was I going to do? What was I thinking about? Oh, I was going to look at our sample size. 91 observations total if we created one big sample. So far, we haven't talked about the central limit theorem at all. But this is interesting. This is actually kind of a two-dimensional bell curve. If you think of like how many dots are close to the center and how they get fewer the farther away you get in either dimension, this is actually kind of like fits a two-dimensional bell curve, which is kind of interesting. So we have our raw data here, all grouped together in a single sample of 91 observations. We have our visual to help us get a faster understanding, and we have a summary statistic, and that's supposed to be that number, which is even closer. And we have our summary statistic, which tells us very quickly that, yeah, we were pretty close to our expected value. So now let's go and let's explore the central limit theorem a little bit. Let's consider not all of our data lumped together, but each of the trials as its own data set. So I can find the average. I'm just going to do this. Should work. Let me just double check. Sometimes when you skip cells, it's fine, and sometimes it doesn't like it. So, okay, oops. Yeah, so these are our averages. So let me make a table that has our sample means, which is when we would want to engage the central limit theorem, right? When we're looking at sample means. We have 10 samples, and we have 10 sample means. They're two-dimensional, but that's okay. This might take me a little bit, but let me just do that. I'm going to change this to, let's put an open circle. Make these ones, how about a plus? Let's try first. Okay, so we have negative 1.27, 15.54, and 30.71, and negative 2.43. I probably don't need this much detail. So I'm going to go faster and not worry about. Oops. 3, 6, 7, 8. There are our 10 sample means. Do they look fairly centered at the same spot? They should, because that's what the central limit theorem tells us, right? Since the sample sizes are a little different, it might not work out to be exactly the same. Take a minute and talk with your neighbor and describe the spread of the individual throws compared to the spread of the sample averages. All right. Compare the spread of the colorful dots to the spread of the black pluses. Which one of those is spread out more? The colorful dots, those are the individual throws, and yet the averages are clustered much more tightly to the expected value. That's exactly the central limit theorem. Individual observations are going to be spread out a lot more than sample averages, because the whole point of a sample average is you've collected more data, so you have a better estimate of what's actually going on. Okay. Can I hear your critique of this visual, Ryan?
The average location on a 2D plane, average distance from a center.
Yeah, so the critique is, well, this way of looking at it, it may work for fast understanding, but if what we're measuring is distance from the center, we'd have to calculate all of these distances kind of mentally, right? So we can actually take this data and with a very simple transformation, turn it into distance data. And I'm going to do that in a minute. But first, let me ask you, would you be surprised if an individual throw landed right here? That's at -20, -20. Would that be super surprising? Why not? Yeah. Yeah, it's pretty close, sure. Gabby?
Looking at that, comparing it to the other data sets that are there, it wouldn't be, it's likely that someone would hit it right there.
Yeah, based on all these other dots, it's pretty likely that a dot might fall here. Yeah. What if it were a sample average, though? Would that be more surprising? Yeah, because that means that all 10 people are hitting kind of in this region. That's surprising given the spread of the data. So a single observation may not be surprising because anything can happen. But a whole sample pulled that far away from the center, that would be surprising. All right, let's do, where did it go? Here it is. All right, let's take our data. I'm going to go back to all of the points as if it's a single sample. And what I'm going to do is I'm going to take each value and I'm going to square it and add it to the other one squared. And then I'm going to take all of that and do the square root. So that's the Pythagorean theorem, right? A squared plus B squared equals C squared. So, oh, that's nice. There we go. These are no longer coordinate points. These are absolute value distances from the center. And I don't want that one. I want. So the average distance from the center was about 33.8 centimeters. Right? If we look at this picture, the average distance, regardless of which way you go, was about 33.8 centimeters, right? Which is about a foot, almost exactly a foot, actually. Let's, this is the average or mean distance. Let's look at the standard deviation of the distance for individual throws. Google Sheets does have a lot of statistical functions built in. So 29 centimeters, almost 30 centimeters. Right, what's that saying is, on average, the throws are about this far away. Right, they could be more, they could be less. Now let's go back. How am I going to do this? This one's going to take a little longer, I think. Yeah. No, it's not so bad. Okay, that's how far away that average throw was there. And so now I can do this and replace it. And then I can average all of the, right? Is that what I want? Yeah. Average all of those. So the average distance of the averages was smaller, right? Because they were clustered more closely. But this isn't exactly what I want. I think just what I want is this. Standard deviation of the average distances is 10.23. So this is a standard deviation of the sample mean distances was 10.23 compared to 30 was the standard deviation of individual throw distances. And the average sample size was about 10. So let's just for fun, let's do 30 divided by the square root of 10. Ah, look at that, pretty close, even though we didn't have good sample sizes. This is the theoretical standard deviation of sample mean distances, right? Where we take the 28.9 and divide it by the square root of 10. And we get something not far off from our experimental standard deviation of sample mean distances. Okay, so I do encourage you to think when you're thinking about what's the difference between individual observations and how they're spread out versus sample means and how they're spread out. I think this picture for me is really helpful because darts on a dartboard or balls thrown against a wall are an image that kind of makes sense to me in a non-mathematical way, right? And so now I think about, well, clustering, how would those darts go? They're going to be spread out a lot more than the average of any given trial. And that's the central limit theorem. That's the end of my lecture. You will be, the rest of lab 2, the continuous data, is kind of exploring this idea with your specific data sets.